Welcome to this DYNANIC demo about scaling network security to 400 gigabits per second and beyond. DYNANIC is a solution that provides throughput of 400 gigabits per second and beyond to FPGA-based SmartNICs of different vendors. Up to now, FPGA solutions required deep FPGA expertise and were strictly limited to the originally designed use cases. But DYNANIC brings a difference in its no FPGA code approach and allows user-end applications to only need to bind to the existing industry standard APIs and benefit from the optimized FPGA processing. DYNANIC supports many manufacturers of different FPGA SmartNICs and provides a unified layer to end-user applications through standardized software APIs. On the right-hand side, we have a high-level look at the DYNANIC solution. On the bottom, we can see that DYNANIC supports a variety of manufacturers such as Silicom, Altera, AMD, or Bitware. In blue, we have the actual DYNANIC solution. The lowest integration level acts as a unique hardware abstraction layer to support a number of different FPGA manufacturers. In the middle, we have DYNANIC's 400 gigabit per second packet processing pipeline. It consists of different customizable modules aggregated to deployment profiles. The final level of DYNANIC is the industry standard API, for instance, based on the Data Plane Development Kit DPDK, through which end-user applications interact with DYNANIC itself. The challenge of increasing network speeds, reaching up to 400 gigs, is a hot topic for many organizations worldwide. What makes this challenge even harder is the security context. Applications performing deep packet inspections do not tolerate packet drops to avoid the introduction of security blind spots. All of this can DYNANIC address. Suricata as the enterprise-level network threat detection engine, intrusion detection system, intrusion prevention system, and network monitoring solution is extended for this demonstration with DYNANIC. Currently, Suricata can reach over 100 gigabits per second, but the problem is that it scales only by adding CPUs, which can be quite costly as shown in the table on the left. If we want to address 400 gigabits per second of throughput, we would need around 20 average servers, which would cost approximately $800,000 over the 5-year horizon. A common technique to address the network load is to reduce the amount of traffic. But as mentioned earlier, in deep packet inspection applications, we cannot tolerate packet loss as uncontrolled packet drop creates security blind spots. This can be seen in the earlier research where even a 3% packet loss for Suricata decreases our visibility into security incidents by 10%. So how does DYNANIC addresses this? DYNANIC addresses this through application-managed advanced parsing and traffic steering capabilities. This means that DYNANIC can directly filter all traffic coming into the card and then deliver only the relevant traffic to the application, such as Suricata or any other deep packet inspection application. Now, in this diagrams, we can see that 400 gigabits per second were filtered to only 30 gigabits per second before being delivered to the CPU. DYNANIC also tackles this challenge through a reprogrammable FPGA pipeline. For this demo, we enlarged the connection tracking table to better suit Suricata. With the reprogrammable pipeline, the solution is completely customizable to application needs. DYNANIC builds on vendor abstract industry APIs, such as the Data Plane Development Kit, and supports many FPGA-based NIC vendors, The current demo will be showcased on the Silicon Network Interface card. In our first demo use case, we have a topology consisting of several instances of packet generators and a single instance of Suricata. The packet generators are T-Rex instances that, in aggregate, can transmit up to 400 gigabits of replay traffic. In our demonstrations, we use 4 instances, 3 for generating volumetric HTTPS traffic, and 1 for the demo traffic, for instance, HTTP or non-standard HTTPS traffic. All of the traffic is forwarded through the network switch to a single 400 qubit port of the DYNANIC loaded FPGA SmartNIC. From this port, all relevant traffic is then delivered to Suricata. In the first demonstration instance, we filter HTTPS traffic directly on the card simply by filtering on port 443. Encrypted traffic cannot be deeply inspected by software like Suricata or any IDS, so Suricata can save resources by filtering this traffic out. We call this a static drop filter, meaning it is defined at the start of Suricata and remains active during the full lifecycle of the application. Switching to the command line, on the left-hand side we see 4 T-Rex instances, one on top of each other on the left-hand side. On the right-hand side, we see the output of Suricata. Let me first start Suricata. And as I start Suricata, we can immediately see the DPDK test PMD language for defining RTFlow hardware rules here, where we see that we filter traffic based on port 443, whether in source or destination. Now I can start all T-Rex instances. We can already observe that each of the 3 HTTPS T-Rex instances transmit at around 83 gigabits per second. And the bottom one transmits at lower speed, the HTTP traffic that's actually delivered to Suricata. Now all instances finished, so we can stop Suricata. In the results, we can observe that the majority of traffic has been bypassed by Suricata, and the difference between the bypassed and the all packet seen is the amount of packets actually received by Suricata instance itself. In this case, it equals to the number of packets sent by the HTTP T-Rex instance. This really shows that DYN can filter all the unwanted traffic on a single port at high speed. But if we want dynamic L7 filtering, we need to go a step further and apply runtime programming to the FPGA cards. This is especially useful if we have encrypted traffic on a non-standard port, such as 8080, and we want to bypass the flow as soon as we detect the encryption. Other use cases include proactively bypassing flows to a known or safe location, or when Suricata identifies network flows as backup streams. Because we don't have this information when initially starting Suricata, the application needs to apply filter rules at runtime to the SmartNIC. For this case, we will use the standard HTTPS instances to provide the bulk of the traffic, again, around 240 gigabits per second, and we will use the fourth TRX instance to transmit HTTPS traffic on non-standard port for encrypted traffic. This means the traffic will reach Suricata, but it will be bypassed as soon as Suricata detects that it's encrypted. And now start Suricata again. I use the same configuration, so again, all HTTPS standard traffic will be filtered by the static group filters, and the dynamic filters will be only used on the remaining traffic. Once again, the top three TRX instances transmit around 83 gigabits per second of traffic, while the bottom one transmits around 14 gigabits per second of HTTPS traffic on a non-443 port. Since all TRX instances are finished, we can stop Suricata to view the results again. And as shown here, Suricata bypassed around 50,000 flows, but it also collected all statistics from these flows as well. Suricata, when bypasses any kind of rule into the hardware, still has full visibility thanks to DYNANIC's counters in the hardware. So we can actually see that, again, the number of packets is the aggregate of all transmitted packets from all instances of TRX. But the difference between packets and bypass packets is the number of packets that got in, but were later filtered by Suricata. In general, it takes around 10 packets for Suricata to detect that it's an encrypted flow, and afterwards Suricata applies the offloading logic on that individual flow. By evaluating the dynamic solution benefits to Suricata in real-world conditions, we come to the following conclusions. While standard server setups for 400 gigabits per second generally require around 20 average servers, DYNANIC helps to reduce this number to only about 4 servers. In this demo, we processed up to 400 gigabits per second of traffic on a single server, focusing on full utilization of DYNANIC bypass capabilities. So while individual numbers depend on the exact solution and situation, in real-life conditions, 20 servers would cost almost $800,000 in the 5-year life cycle, whereas the DYNANIC solution with 5 times server reduction costs only $200,000. Additionally, because Suricata can configure the FPGA SmartNIC at runtime, the card supports L7, Layer 7 DPI processing and remains customizable at any time in the future thanks to DYNANIC. If anything changes in the networking space, the firmware can be updated to process higher speed, modify the processing capabilities, or support newly introduced network protocols. That That's all for now. Thank you for your attention, and if you have any inquiries, please do not hesitate to contact DYNANIC. Thank you.